So we're starting off here with just a review of Earth's interior. And so when we think about plate tectonics, when we think about these pieces of crust that are moving around on the surface of the Earth, we're really referring to what is known as the lithosphere. So the lithosphere is comprised of the very uppermost part of the mantle, known as the lithospheric mantle. So that's kind of what the crust, the hard part here, is floating on top of. So we have the lithospheric mantle, we have our rigid crust at the very surface of the Earth, and these two combined make up the anatomy, if you will, of a tectonic plate. So these are the things we're looking at when we start talking about these plates. Now, if we zoom out and look at a world map, we can see here that there are lots of different plates. So here each color is a different plate, and they're different shapes, they're different sizes, and they're all moving around relative to one another. So whenever we look where one plate meets another plate, we refer to this generally as a plate boundary. And depending on whether these plates are going towards each other, going away from each other, sliding past each other, we can get various types of plate boundaries. So we're going to start going through our plate boundaries here. And just in general, we have three big groups of our plate boundaries. We have our divergent plate boundaries, convergent plate boundaries, and transform plate boundaries. So we're going to break these down, talk about them individually, and start relating them to the exercises we're going to be working on in lab today. So our first type of plate boundary here is a divergent plate boundary. So when we think of divergent plate boundaries, we're thinking we have two plates that are drifting away from each other. Well, how does this happen? The mechanism that causes these plates to start to drift away from each other starts down in the mantle. So down in the mantle, we have a plume of very hot material. It's a little bit less dense than what's around it, and so it wants to rise up to the surface of the Earth. Well, what happens is that liquid magma comes up to the surface of the Earth, and it's going to start to cool off, and it's going to solidify and turn into a solid rock. Well, this process continually happening, so as these rocks drift up and cool off, we kind of describe this sometimes as a conveyor belt type of mechanism, because as we're constantly creating new rock along this crack in the earth, creating new oceanic crust, the crust is then going to start to push pre-existing crust off in either direction. So we start to push things off in both directions away from that, what we call a spreading center. So whenever we talk about divergent plate boundaries, oftentimes you'll hear the word mid-ocean ridge or spreading center to describe what's happening at these type of plate boundaries, because what's happening is we are literally spreading the crust away from each other. The mid-ocean part comes into play because oftentimes these are typically found in the middle of ocean basins. So you have one out in the mid-Atlantic, we have some out in the Pacific, and so we have two plates that are starting to drift away from each other, and these are specifically oceanic crust. So one of the applications we're going to work on in lab has to do with these divergent boundaries, looking at these spreading centers. And we need a little bit of background here. We're going to be talking for the next couple of slides about this idea of paleomagnetism. So whenever we think about these divergent plate boundaries, we have liquid rock that's coming up, it's cooling off, and the resulting rock is going to be an igneous rock. So oftentimes we think about these happening at volcanoes. That's kind of what our image depicts here, but this is also applicable to our spreading centers. So the idea of paleomagnetism here is whenever we look at igneous rocks, they can naturally have a little bit of magnetic minerals in them. So minerals that naturally want to align themselves with Earth's magnetic field, just like a compass or a magnet would do. And so whenever, for instance, when we look at the volcano here, whenever that liquid material comes up and starts to cool off, those magnets have not yet aligned themselves with Earth's magnetic field. So whenever a rock is still a liquid, it's too hot, and they're just pointing in all different directions. The magic here comes whenever we go from that liquid phase to a solid phase. When we go from that magma to a solid rock, at the point where they turn solid, those magnetic minerals are naturally going to align themselves with Earth's magnetic field, just like a compass. And the reason that this is useful to us is that at our spreading centers, we're constantly creating new oceanic crust. And so basically, our oceanic crust is recording trends in Earth's magnetic field over time. So I said that Earth's magnetic field is generated by the liquid outer core. So it's liquid metal that flows and it generates a magnetic field. Well, that magnetic field uh, periodically will actually flip pretty much 180 degrees, flip over on its head, and we get these sort of opposites of magnetic minerals being reserved in our igneous rocks. And so again, if we look at this picture here, we're thinking about these spreading centers. We're creating new oceanic crust, we're creating these new igneous rocks in the middle of our oceans. And if we look right where our spreading center is, this is where our youngest rocks are going to be. And again, that conveyor belt model, if we start to create rocks in the center, we keep creating them over time, and they're going to be pushing pre-existing rocks out symmetrically on either side. So how we relate this to our paleomagnetism, relating it to those magnetic minerals, our ocean floor is basically a history book recording information about Earth's magnetic field back and back and back through history. So if we look here, this is what we'll call time one. So this is some time in the past, and we had our spreading center, and we're creating new rock. Well, we zoom forward in time a little bit, and here, the rocks that we were actively creating in the center have been pushed away. And looking forward, maybe this is maybe our present time here, we have these alternating stripes, if you will. So we have these stripes of different magnetic information being recorded in those igneous rocks on the ocean floor. So we have these stripes of magnetic minerals, crust is carried away in both sides, and we're recording basically the history of Earth's magnetic field in these oceanic crust stripes. So how we're going to relate this idea to our exercises for today is we're going to be using these magnetic stripes. They're going to give us information about the age of our rocks. And we're also going to, we've got a lot of map skills that we've built up, right? If we can find the age of our rock, so the time that the crust was created, we can combine that with distance. So we can go to a map and we can measure distances on a map, right? And what we're going to be doing with one of our exercises is we're actually going to be calculating the rate at which a mid-ocean ridge is spreading, or in other words, the rate at which we're creating new oceanic crust at that mid-ocean ridge. And so just in general, we have a rate equation here. So I've kind of keyed it up for spreading in particular. But anytime we calculate rate, it's going to be a function of distance divided by time. So here for our spreading rate, we're looking at measuring the distance from our mid-ocean ridge and combining that with the age of our rock. That's where we're going to get our time element here. And what this will tell us is how quickly or how fast that mid-ocean ridge is creating new crust. So I put a little warning on here. We need to be careful with our units. We're going to go through an example problem together later, but just in the back of our minds, we're doing calculations in lab today, so we always want to keep up with those units and be mindful of what units we're using. Okay, so everything up to this point has just been talking about that first group of plate boundary known as a divergent plate boundary. So we're creating new oceanic crust, and those two plates are moving away from each other. Now, oftentimes what we'll see is along plate boundaries, we will have two plates coming together, so they're moving towards each other. We call these convergent plate boundaries. And depending on what type of crust, oceanic, continental, mix of both, depending on what kind of crust we have, we'll put our convergent plate boundaries into three different categories. So if we look here, we have one kind of subheading, and we say here we're looking at subduction zone types of convergent plate boundaries for these first two. So what that means is we have two plates running into each other, and one of them is going to be forced underneath the other. It's going to start to drift down inside the earth, and it basically gets recycled down in the mantle. So our first scenario here is if we have oceanic crust colliding with a piece of continental crust. This is going to produce our first scenario here. So we have our oceanic crust, and the rule of thumb with an oceanic continental collision is that our oceanic crust is always going to be the one that subducts. So oceanic crust has a different chemistry than continental crust. It's a little bit more dense, and that makes it a little bit heavier, and so that's naturally going to make the oceanic crust go underneath the continent. And so our lithosphere on our oceanic crust is always going to be the piece that is subducted. So as we are subducting this piece of oceanic crust, it runs into the continent, it starts to go down into the mantle. Well, I'm sure in class you've learned about your geothermal gradient. The farther we go inside the Earth, the hotter it gets. Well, as this crust is going down into our mantle, it's going to start to heat up. And what happens is we're going to partially melt a little bit of our crust here, or a little bit of our oceanic crust that's going down. And whenever talking about densities, when rock melts, that causes it to have a little bit lighter density or a little bit lower density than the rock that surrounds it. So as we start to melt that oceanic crust, that lighter material is going to rise up through the crust, and it's going to manifest itself as volcanoes along the edge of our continent. So a real life example here would be out in the Cascade Mountains, out in Oregon, Washington State. A lot of those really tall mountains are actually volcanoes, active or dormant, and they're being fed by this subduction of a piece of oceanic crust beneath our continental crust. So when we see this chain of volcanoes, we call this a volcanic arc. Now, one of the physical features we can look for on the surface of the Earth to know that we have a subduction zone is this word right here. We call them a trench. So where we have our slab subducting beneath our continent here, that's going to create this little V-shaped low spot on the bottom of the ocean known as our trench. And so that's a physical feature on the surface of the Earth along with our volcanic arc that can indicate to us that down in the subsurface we have a piece of crust, oceanic crust, that is subducting. Now we're still talking about subduction zones here, but sometimes we have instances where we have a piece of oceanic crust colliding with another piece of oceanic crust. And so that's our second diagram over here. So what happens in this case is we have oceanic crust running into oceanic crust, and we're still thinking about density here. And the rule of thumb is that the older piece of crust has cooled off for longer, it has a higher density, and so the older, colder crust is always going to be the piece that subducts. Well, as we subduct our lithosphere, it's still going to melt as it goes down into our mantle. A little bit of that is going to rise up, and we form volcanoes on the surface of the Earth due to that liquid rock. And here, since we're out in the middle of the ocean, our oceanic-oceanic collision, it's going to produce a chain of volcanoes out in the ocean, usually fairly parallel to the subduction zone here. If we look, we still have that same physical feature. We still have our V-shaped trench down on the bottom of the ocean to indicate we have a subduction zone. We have our volcanoes, but in this case, they're going to be volcanic islands. So we usually refer to that as a volcanic island arc. Now we look down at the bottom, we have our third type of convergent plate boundary, and here, process of elimination, our only combination left is to have a continental collision. So we call this a collisional zone as opposed to a subduction zone because when we have continental crust colliding with continental crust, neither one of these pieces is going to want to subduct. So continental crust is generally much thicker than our oceanic crust. It's going to be more rigid. There's no density difference here. And so when two continents collide, neither one of them is going to want to subduct. And what happens is that rock on the surface of the Earth, that continental crust, is going to be forced up into the air. So basically they're like two rams butting heads, and what happens is it's going to produce very large mountain ranges. So these rocks run into each other, there's nowhere for them to go but up, and so they start to build up into these very large mountain ranges. So if we look at a geographic example of one of these in the modern, this is how our Himalayan mountains form. So we all know the tallest mountain on the Earth, Mount Everest, is out in our Himalayan mountains, and that is where the Indian continent, it's actually a plate, it's its own lithospheric plate of continental crust, is colliding with Asia. And again, neither one wants to subduct because they're thick and old and cold. And so that's how we have produced those Himalayan mountains. So convergent plate boundaries, we have two plates running together. They're either going to subduct if we have some element of oceanic crust, and we have two various situations there, or if we have continental crust, we're going to see very large mountain ranges because those rocks get forced up into the air. Last but not least, we have our transform plate boundary. So transform plate boundaries occur when we have two plates sliding past each other. So we don't have any up and down motion, we just have this side to side motion here. Oftentimes we associate our transform plate boundaries with our mid-ocean ridges. So mid-ocean ridges are divergent plate boundaries, right? We're spreading, we're creating new crust, but oftentimes we see that those mid-ocean ridges are not linear. They're not directly connected in a straight line. They're going to be offset, and everywhere they're offset is going to be a transform plate boundary connecting them. We can also get these on continents. So the San Andreas Fault here is probably the most famous transform plate boundary that we know. So one of the byproducts of these different types of plate boundaries is really any time, if you think about having a giant slab of rock colliding with another slab, subducting under another slab, sliding past another slab, you can imagine there's going to be a lot of friction. There's a lot of force, there's a lot of pressure between those two giant slabs of rock. And so we get all of this friction as those plates slide past each other in their various forms. And so one of the sort of consequences, I guess you will, of plate tectonics is that oftentimes we experience large quantities of potentially very high magnitude earthquakes along our plate boundaries. So here we have a side-by-side map. We have our plate boundary map up here that we saw before. At the bottom, we have a map that shows the same world view, the same area, and if we look really close, what we have is we have a whole bunch of tiny red dots. So all of these are little individual red dots here marking the epicenter or the location of where an earthquake has happened. And so they are not specifically for our plate boundaries. This is showing earthquakes everywhere, so we have some away from our plate boundaries as well. But what we notice is we have a very high concentration. We have these very big masses of these red dots accumulating along our plate boundaries. So we can trace these plate boundaries out and we can look down here and we see associated earthquake activity along those plate boundaries. So again, if anytime we have these big rocks sliding past each other, oftentimes they're going to get stuck. There's just so much mass, so much friction that they kind of stick for a little while. They build up potential energy, and eventually they're going to surpass the capacity of the rock to withstand that pressure or that force, and the rocks are going to kind of jump and move past each other. And whenever that happens, that release of energy is what we call an earthquake. So the cool thing about this is we can actually use earthquake locations to identify plate boundaries. So down here, if we weren't aware of where our plate boundaries were on this bottom map, it's almost quite easy to go along and look for where we have these clusters of red dots, clusters of earthquake epicenters, and start to draw out lines where we can see kind of these linear groupings of those clusters of those red dots. And sure enough, if we compare that to a plate boundary map, they are related. We can use those earthquake locations to help map out plate boundaries. All right, so we're going to switch gears here towards the end of our PowerPoint. So this is going to be related to another activity that we're doing. So two of our activities are going to be related to plate boundaries. And here we're still going to be studying our plate tectonics, but we're going to be looking at a slightly different feature. This feature is known as a hotspot. So hotspots, our definition here, these are stationary heat sources from the mantle. So the word stationary here means that our hotspot, these hot places down in our mantle, are not moving. So down in the mantle, we don't have plate tectonics. We don't have our mantle moving around like we think about our plates moving at the surface of the earth. And for a hotspot, again, it's this hot, extra less dense area down in our mantle beneath our crust, and it is not moving, so it's staying in one spot. Well, when we have this extra hot material, we saw earlier with our island arcs that whenever we melt solid rock, it's going to lower the density. That liquid rock is going to want to rise up. It's less dense, so it wants to float up to the top. And so this melted rock floats up and breaks through the crust, and we form volcanoes on the crust above a hotspot. So our hotspots are going to produce magma, extrude onto the surface. We call that a volcano. Now, the interesting thing here is that when we're talking about these volcanoes, they are formed by a completely different mechanism than the ones we saw before. So before, our volcanoes were being driven by subduction, melting that crust and it rising up. Here, we are generally nowhere near a plate boundary. So usually we're really far away from our plate boundaries. And so this is this is volcanism that is not produced by subduction. So we're still getting the same end result. We're still getting these volcanoes on the surface of the earth, but it's being driven by different forces here. So I put it up at the top, stationary. I've set it down here. The hot spot is not going to move. What happens is that the lithosphere, these plates, are going to slide. They're always moving, right? And the lithosphere is going to move over the hot spot. So what that does is it produces a chain of extinct volcanoes. So generally we will have one active volcano, and then if you look back, you can usually see a chain of little islands. They're volcanic islands, but they're no longer active. They're not actively being fed by a magma. They're not erupting. They're extinct volcanoes. And what happens is that these volcanoes, as we go farther and farther away from the active spot, they're going to get older and older. Well, that's because, again, our plate is moving over top of the hot spot, and in the past, we were actively having volcanism at those islands, and the plate's going to move off in one direction, and so the farther we go away from where the volcanism is today, those hot spot tracks, those extinct volcanoes, are going to get older and older away from where they're actively erupting today. So two well-known examples here. These are actually US examples, which is really cool. We have our Hawaiian Islands, and then we also have Yellowstone. So we've all heard of the supervolcano at Yellowstone. Well, what's feeding that volcano is one of these hot spots, one of these extra hot, low-density places down in our mantle. So here we're going to zoom in, we're going to look at the Hawaiian Islands example. And so what happens here, again, we have our mantle plume, we have this extra hot material down in our mantle. It melts our crust because it's extra hot, right? And that melt rises up and it produces a volcano on the surface of the earth. So if you've been to Hawaii, even if you haven't, we have our quote unquote big island, just the island of Hawaii, where we still have active volcanoes today. So last year, early spring 2018, there was a big breakout of volcanism on the Big Island here because it's still actively being fed by this hotspot. Well, if we look off at the other Hawaiian Islands, they're all a little bit smaller. They all kind of make this chain, if you will. And what we see is our Big Island is still active, so it's basically 0 million years old. If we go over to Maui, that's 1.3 million. Molokai 1.8, Oahu 3.4, so on and so forth. And so what we're seeing is that trend I mentioned before, that we have our active volcano here and they get older and older. These islands get older and older as we go away from the active spot. And that is because our hot spot's staying still, and here the Pacific plate, and we have these arrows here showing us that our Pacific plate is moving. It's moving over top of our hot spot, and it's producing these volcanoes on the surface of the earth. So how are we going to tie this in to our activity? Well, we're going to be using the ages of these volcanoes. We're going to be using a map to measure distances. Maybe this is ringing a bell. Earlier we were talking about rate. Rate is distance over time. Well, we can use our hotspot tracks to help us calculate the rate of plate motion again. So before we were calculating the rate of plate motion at a divergent plate boundary, the rate of spreading at a mid-ocean ridge or spreading center. Well, here we're calculating the rate at which a plate is sliding over the top of our hotspot. So the hotspot stays still, the plate travels over top of it, and we get this preserved record. In this case, in Hawaii, we get our little Hawaiian Islands that are preserving where this hotspot has created volcanoes in the past. So it's showing where the plate is moving. So we'll get into a little bit more of that whenever we talk about our exercises at the end. So here, if we zoom out again to a world map, there are about 100 known hotspot volcanoes around the world today that we've identified. Now, if we start to look at the map, one thing we might notice is that most of these little red tracks, most of where we're seeing these hotspot chains, are out in our ocean basins. Well, it actually happens for two reasons. If we think back, our oceanic crust is much thinner than our continental crust. So when we have one of these hot spots down in our mantle, it's much easier for the mantle to melt the thin oceanic crust to allow that magma to rise up through the crust in the ocean, as opposed to our continents have very, very thick compared to our oceanic crust, the crust on our continents is much thicker, and so it takes a whole lot of heat to be able to melt up through continental crust. Also, whenever we look, when we look at a map of the ocean floor, it's pretty obvious. If you think about, out in the ocean, it's pretty flat, and if you have a chain of mountains on the ocean floor, that's going to grab your attention, right? So it's easier to pick out these hotspot tracks on our ocean floor just because it's so flat otherwise, generally, and so they kind of jump out at us. Well, we do have a few notable examples within our continents. So we mentioned before our Yellowstone hotspot. It's a big super volcano, right? It's a very hot hotspot there because it's able to melt through the center of our continent, to melt through several kilometers, tens of probably, I don't know, 30 or 40 kilometers of continental crust here, and produce magma at the surface. Now, Yellowstone is I won't say inactive, it hasn't erupted in a while. And so we might not think about it like being a volcano, but it's actually being fed by a hotspot. Also, out here in Africa, we have several areas where there are hotspots located and identified beneath the African continent. And that's because we have what's called a rift zone here, where the mantle processes are trying to rise up and basically split Africa into pieces. Out here in East Africa, it's called the East African Rift Zone. So we're basically trying to create a new spreading center or a new divergent plate boundary underneath the continent of Africa. One of the byproducts of that is going to be some of these hotspot volcanoes. So we're going to be doing an exercise related to looking at hotspots and using information we can glean from hotspots to, again, calculate rates of plate movement over the top of our hotspot.